All right, hello everyone. So today we're going to be looking at arc length. And specifically, how do we calculate the arc length from any point from a to b of some function f of x? So why don't we look at this more visually? So let's say we have this function on this graph. Let's see, it's a two-dimensional plane. And say we want to go from this starting point of a to, let's say, this ending point right here of b. And we're just going to call this function, this is f of x. And so the question that I'm asking is, this length that I'm outlining in blue, what is that length? I'm going to call that L. L is going to be our arc length, the length of this arc that we have here. So if we want to use calculus in order to figure out a general solution for this, what we can do is split up this arc into tiny, infinitely small lines here. So I can take just any arbitrary part of this graph. Let me change to a different color, make it easier. Any arbitrary part, and I can scale it up over here. And so scaling it up, this is pretty much going to look like a straight line where we are, because we're looking at infinitely small. And so what we can say about this line is on this portion right here that I've circled, we're going to have two dimensions. So we're going to see an infinitely small portion on the x, which we'll call dx. And we're going to see an infinitely small portion on the y, which we'll call dy. And so in this triangle right here that we're going to make, we see on the x-axis here, this is dx. And on the y-axis here, this is dy. And now what do we call this hypotenuse here? Well, if the entire portion of this arc is L, we'll just call this dl. A small chunk, an infinitely small chunk of L, our bigger portion of the arc length that we want. And so from this triangle, now we can use Pythagorean's theorem. A squared plus b squared is equal to c squared. And so we can see that our c squared here, I'll rewrite this. So c squared is equal to a squared plus b squared. Just so now as I write this function, it'll look a little bit more clean. Where our c here is our dl. So we're going to have dl squared is equal to, now a squared, it can be any arbitrary value. I'll just say that a is going to be our dx squared plus b. The b must be the other length, side length of the triangle, and that is going to be dy squared. And so now where do I go with this? Well, if I'm looking to find a function that'll help us calculate this arc length, first thing we need to do is isolate this dl here. So I'm going to take the square root on both sides. And this is going to give me dl is equal to the square root of dx squared plus dy squared. And so now this is a bit of a tricky part here, but what I'm actually going to do is I'm going to take out a dx squared from both of the terms inside of here. And so what I'm going to have here is dx squared times 1 plus dy squared over dx squared, like that. And you see if we distribute this dx squared term back in, we'll get the same equation, so we know that what we have is true. And the reason why that we're taking out this dx squared is because we want to have some function, if we're looking to have an end game of reaching some some integral. We're looking at the integral from a to b of some function f of, we'll just say this is f of x dx, like this. We want to have this dx term out here. And so the only way we can get that is by taking out a dx squared, and you'll see here we're going to have this square root with a square term in here, and these two terms are multiplied together, and so we'd be able to take out that dx squared. And that's exactly what we're going to be doing in this next step here. And so we're going to say dl is equal to, and we're going to be able to take out that dx squared from the square root. So dx times 1 plus, and then if we just want to simplify this, we can say that dy squared over dx squared is dy over dx, all of that fraction squared. And so dy over dx, this fraction squared. And now by doing that, this actually helps us again with another simplification, in which we could say, hold up, wait a minute. dy over dx right here, dy over dx is just equal to f prime of x, right? It's equal to the first derivative of our function f of x. Again, just to remind you, the function that we're using to describe this line right here. And so, continuing on from there, in that case, what we can write is dl is equal to dx times the square root of 1 plus, and now we can write f prime of x squared. And now if we want to get this in terms of looking like our integral over here of this f of x dx term, then what we're going to need to do is we're just going to reverse the order that we're using of this dx and the square root. And we're going to say that dl is equal to the square root of 1 plus f prime of x squared dx, use that commutative property. And then what we're going to do now actually is we're going to be able to take our integral. So what this equation right now is describing is that we have an infinitely small length here, an infinitely small length, I should add arc length, infinitely small arc length, and what we have here is some function f of x and some width of dx. Some width here. And so what we're in essence going to be doing is going from A to B. We're going to be traversing along very fine increments of size dx, following this function f of x, and we're going to be creating this infinitely small line here. And so in a sense, it'll look like this, where you have a small line, small line, small line, small line, small line, small line. I guess if I want to change it up to make it look a bit more curved, might be something like small line, small line, small line, small line, small line, small line. And all of these small lines here, these are going to be like DLs here. So another DL that we're adding. Right here is another DL that we're adding. And what we want to do is we want to sum these up. We want to take the sum of all these DL terms. And what exactly are we doing with this? We're creating the Riemann sum. And how we define the Riemann sum is with the integral. And so that's where our integral is going to come from. So we're going to take the integral of DL is equal to the integral of our f of x term here. 1 plus f prime of x, that term squared, dx. But now we need to look at the bounds, right? Because now we need to think, what exactly are the bounds here? Well, we know that for our right-hand side, that we're going to start from A and go to B. That isn't too hard to understand from seeing from the visual here, where we're starting from A, we're going to traverse through this line of f of x here, and then we're going to end at b. Start from a, traverse through the line, end at b. That gives us the bounds of this integral here, where we're starting from a, ending at b. But what about this dl here? Well, in order for us to properly apply the integral to both sides, we need to have similar bounds here. And so what we're pretty much asking is that, okay, at our start of a, what is L equal to here? And our ending at b, what is L equal to here? Right? Because we're saying, what are the bounds? What length are we going to start with? And then what ending length are we going to end at? And so by looking at the visual, we can see that once we start from A, actually let me remake this again to make it a bit cleaner, a bit nicer to see. Just draw this curve here. Once we start from A, what exactly is our length, right? If we want to slowly add up all these lines here, well, when we start from A, our length is equal to 0, right? Because we haven't counted up anything on this line, on this arc length, or on this arc, I should say. And so once we're at A, our equivalent starting bound for DL is going to be 0. And so now we ask, okay, what happens at our ending length of B? Well, at our ending length, we've summed up all the DLs up until the point in which we reach B. Once we reach B, what is the length that we have here? Well, it's everything before it, which is L. And so we're going to go from the integral from 0 to L dl is equal to the integral a to b, the square root of 1 plus f prime of x squared, times dx. I just realized I've been missing some parentheses here. So please take note of that. And there we go. And so we can get our final equation by then simplifying this term here, because we know that the integral from 0 to L dl is going to be L evaluated from 0 to L. It's equal to the integral from a to b, the square root of 1 plus f prime of x squared dx. And the value of L integrated from 0 to L is just L minus 0. It's equal to the integral from a to b, square root of 1 plus f prime of x squared dx. And finally, we know that L minus 0 is just L. So L, the total arc length, is equal to the integral from a to b, the square root of 1 plus f prime of x squared dx. So the total arc length is equal to all this term, which is equal to the Riemann sum, which this is just the integral. The Riemann sum of this function here of 1 plus the slope at x squared multiplied by dx. This your width here. And so that's about it. That's proving that the arc length of any point from a to b of any function is equal to the integral from a to b times of the square root of 1 plus f prime of x squared dx.